Probability actually can be quite hard. I've talked about this in other places. Our minds aren't perhaps suited for thinking about these things, and certainly our gut instincts can sometimes take us entirely the wrong way. That's one reason why we have mathematical probability, why we do it with maths, is because it doesn't just come magically into our heads. Sometimes means that if you're faced with certain types of problems, the thing to do is go and talk to those people who are the professional mathematician, the professional probability person, not just try and do it yourself if you're not like that. But I'll also try and give you a little bit of a clue as to a technique that I certainly find helps me turn what are these difficult problems into things where suddenly my sort of common sense can help me make sense of it. In order to do this, I'm going to start off with the Monty Hall problem. Now, you might have come across this before. This came from a quiz show. I think it might have been as far back as the 1950s. And at the end of the quiz show, they probably had lots of other bits as well. But at the very end, there are these 3 doors, and the person has 3 doors. And behind one of the doors, I don't know whether they use models or images or whether they were just very big doors. But anyway, behind one of the doors was the star prize, which is your car, right? So you're going to have your car if you have one of the doors. But behind the other 2 doors are goats, and you've lost. And you get to choose one door to open. So you're the contestant and you open a door. The question is, then the quizmaster comes and says, hey, okay, you chose this door, and then opens one of the other doors. Of course, the quizmaster knows what's behind the doors and will always open a goat door, never opens the car door. That would seem a bit unfair. Opens one of the other doors, always got that you haven't chosen, which has a goat behind it. And then says, okay, you chose, and say you'd originally chosen door number 1. And the quizmaster says to you, would you like to change your mind? Now, the question is, should you change your mind? There's one argument that says, well, nothing's changed. You had a 1 in 3 before, 1 in 3 after. Another says, well, there's only 2 doors now, but then still they're both equal, right? So does it make any difference if you change your mind? The interesting thing is even mathematicians find this hard and disagree about it. I mean, there is a right answer, but their common sense, even as mathematicians, gets wrong sometimes. Some of them get it right, but not necessarily for the right reasons, and some just get it wrong. I won't tell you what the answer is initially, but what I'll do is tell you how. Well, we will tell you the answer is in a moment, but before that, just a way of what might make it easier. So that was 3 doors. Imagine it was 1 million doors. So it's a very, very, very big studio, and the doors just disappear into the distance. And the quizmaster says to you, choose one of the 1 million doors, right? And only one has a car behind. All the other 999,999 doors have goats. So you choose one of the doors. And come on. It's the likelihood of getting the car is, that. And then what the quizmaster does is opens 999,998 of the other doors, but only ever opens ones with goats behind. So open. So there's only 2 doors left. One is the one that you'd originally chosen, and one is one other door. So now, do you change your mind? I think it's pretty obvious, isn't it, that when you first chose your door, the likelihood that you chose that car is zilch. Right? The car is bound to be in one of the other doors. The quizmaster's opened all the ones apart from one, so it's pretty obvious that the car is very, very likely. I mean, you might have had that 1 in a million chance to start with, and you change your mind. So by changing the number, by scaling it up and making it really, really big, so rather than 3, actually, you change it to some other number, suddenly what seems a bit weird and not quite sure becomes absolutely obvious and very clear what to do. And now, of course, just because it's true of 1 million that you change your mind doesn't necessarily mean it's true of 3, but it certainly helps you both get a better gut feeling for the problem, but actually also is the way that you can get to the start of trying to analyse it properly often, and verify that your reasoning processes make sense. Because if the reasoning process you used for 3 doors fails for 1,000,000 doors, then it probably wasn't a very good reasoning process. So that can help a lot. Now, the Monty Hall thing was a quiz show. That's a show. However, this is a very, very real problem. This particular kind of problem happens a lot, particularly with court evidence. So a classic, which I said is different but it has a similar sort of feel to it, is DNA evidence. And there's been a lot of issues about DNA evidence. So say a DNA match is accurate to 1 in 100,000. 2 cases come to court, right? In one of them, person's been murdered after having a big argument with a friend, and then the person's been murdered. So obviously the finger of suspicion points to the friend with whom he had the argument. The friend's DNA matches DNA they found on perhaps the murder weapon at the scene. You take this evidence to court. Pretty damning. The second example, very, very similar. A person has been murdered. This time there's no argument. The only clue is DNA evidence at the scene. The police then take the DNA evidence, match it against a DNA database and find a match. They take that person to court. So in both cases, what the evidence is brought to court is, here's a person, there's a DNA match, and it's a 1 in 100,000. But I think it should be obvious, but it has been confusing in courts, that in the first case, that's a pretty damning bit of additional evidence. The second case is problematic. Now, to see why it's problematic, there's 2 things you could do. One is to just imagine that database. If there's 1,000,000 people in the database, then you're probably, on average, you're probably going to get 10 matches. It's a 1 in 100,000 match. So it tells you nothing. But if you change the scale again, so with the Monty Hall, I made the number get bigger. Now let's make it smaller. So say the accuracy wasn't 1 in 100,000, say it was 1 in 100. Well, the DNA match at the scene wouldn't be as damning for the friend, but it would be good additional evidence that help you restart to think that, yes, perhaps it was the friend. But if it was a 1 in 100 match, then it's fairly obvious. If you go to a database and find somebody that matches, it tells you nothing at all. So again, so this scaling thing can help in both directions. So in the end, though, part of this is to say, that's a good heuristic that can help you. Part of it is to show that these things can be complicated. Now, DNA evidence, there have been cases recently that have been turned over where evidence has been presented, courts have convicted people, sent them to prison, and then realised afterwards that they'd basically made a horrible mistake on this kind of argument. So when you're doing your work, if you get faced with difficult and complicated issues, in the end, if you can't sort them yourself, and perhaps this might help you, the techniques might help you here, but if you can't, go and ask somebody, because stats is complicated and probability is pretty hard.